All right, good morning, everybody. For those of you who weren't here day one when I hopped on, you saw my face and my voice for a minute. I'm PLANCHER. I'm a assistant professor at Barnard College, Columbia University, and I've had the privilege of working with Marco and Marcelo and Jeremy and all the other folks to help arrange this stuff over the past couple of years. In the background, I do want to give a huge shout out though to Marco, Marcelo, and Jeremy and everybody else who's been running this all week and who's been really driving this for the past couple of years. I don't think we would be remotely close to being able to have events like this without all of their support and everything like that. And I assume you can like see my screen and you can hear me because I'm not getting like panic messages from anybody else. Cool. Thumbs up, somebody. Awesome, great. So today is day 4. Today we're doing the TinyML show and tell. I'll just kick it off and then I'll turn it over to a bunch of other folks who have lots of interesting projects and you don't have to hear from me anymore. So what is show and tell? Where can we find show and tell? How can we learn more about show and tell? So if you go to the main tinyml-edu.org website, you'll see across the top there's a tab for show and tell that you can click on, or you can just go straight to the link that I put at the top, just /show and tell. And what is a show and tell? This is the text on the website, basically the high level summary is show and tell is any sort of project related to TinyML. It doesn't have to be perfect. It doesn't have to be done. What we've been doing is sort of running a series every month, couple of months to try to allow folks in the community to share, to show and tell about what they're working on. And to get some feedback from the rest of the community or to ask questions. So if you have a project where you've gotten the first half of it figured out and you're really excited and you want to talk about all the ideas you have for the second half, but you don't actually know entirely how to get there, this is also a great venue for that. Or you've got this amazing project and it's fully done. For today, I think we'll see a mix of progress. And for today, we did want to note that we had way more people submit amazing, awesome, and exciting projects than we could possibly fit into one day. And so we invite everybody who submitted things but can't present today to consider presenting at a future show and tell. And towards that end, if you want to see past show and tells, literally if you're on this page and you scroll down, the next thing you'll see is all the recordings and notes about who gave past show and tells and links to all those video recordings and what they talked about. But also we will be sending out a call for future show and tell talks soon, and especially to the folks who submitted to talk today, but there wasn't any room, we'd really invite you to consider giving a presentation in the next few months because we just thought there were a ton of really exciting things. And thanks to Jeremy for coordinating the show and tells. So that's sort of a little bit of context. What are we going to be talking about today? Lots of really exciting things from all over the world. We've got a couple presentations from Africa, from South America, from Asia on lots of different topics, from how do you make a TinyML personal trainer, to how do we do crop disease detection, to making poultry farms and digital signal processing and all other rainfall estimation, sleep apnea, animal tracking, language recognition, all over the place. I probably missed one because I jumped around and didn't go in order, but we will hear about all of them today and it is going to be really exciting. And I just also wanted to make one shout out to Seed Studio because Seed Studio is going to be supporting the top 3 presentations, which is really exciting to us. So thanks to them for doing that. Since there'll be a lot of presentations, since we'll be going through a bunch of them, I'm sure there will be a ton of questions today. And as Marco has been saying the past couple of days, please join the Discord. Please post questions on Discord. It's nice and it sticks around instead of Zoom chat, which kind of disappears. And so it'll be a lot easier to manage the questions, respond to all the questions, and it will provide a place for everyone who's giving these exciting presentations today to respond to you later, maybe follow up, maybe it starts a conversation. We hope that these presentations are inspirational for a lot of you about lots of different things you can do with TinyML. And for those of you that are presenting, we hope that this also is an opportunity where you can get some feedback from the community and hopefully make your projects even better. And so kind of with that, that was sort of all I wanted to do in terms of a kickoff. And I know for today, Marco has got a lot of pre-recorded presentations that we're going to share just to make sure we can maximize bandwidth and all those sorts of things. I think one or two of them might be live, but the Q&A will be live. And so once we finish all those, once we finish each recording, we'll open it up for that as well. And so that was sort of all I had. And I think with that sort of context, maybe 3 minutes early, I could toss it back over to Marco to start the first presentation.
Okay, super. So let's start with the first presentation.
Smart Poultry Farm.
Good.
TinyML-based disease detection system through audio signal. A case study at this workshop, 2023. There's an increase in consumption of animal products such as meat, milk, and egg. However, there's a decline in production of these sources of protein. There's also a growing concern of increasing food production by 25% to meet the need of the growing population. Major sources of protein, which is a poultry farm, are faced with health challenges, which leads to economic loss in poultry farm. Hence, the need for early detection and prevention of poultry-related health challenges. Due to paucity of publicly available data sets on environmental sound classification, and the fact that most studies so far focus on specific species of chicken, with many of these data sets not publicly available in open source repository, this work is set out to achieve gathering and annotating data sets of poultry vocals and acoustic under varying weather conditions for the purpose of stress detection and prevention to mitigate loss and thereby maximizing profit on poultry farm. These are our objective: developing of poultry chicken vocal data set for machine learning research, extraction of the features from this data set, training of machine learning algorithm with these features extracted, developing a classification model, also developing more mobile-based poultry health predictive system, as well as deploying this system on poultry farm to see the performance. Now, to be able to achieve this is the architecture where chicken sounds are extracted using the necessary module from the poultry farm, and features are extracted from this sound, which are used to train algorithm. The algorithm, the model is able to classify the poultry status, whether healthy or not healthy. And if it's not healthy, the kind of disease the poultry is facing, and probably provide solution or treatment information for the farmer so that the farmer will know the right thing to do. We kept a poultry farm where we have our chicken from day old. We have them while they were at 2 weeks, and while they were at 8 weeks old. A total of 100 broiler chicken were collected and divided into 2 groups of 50 each. One of the groups were treated for diseases while the others were not. Now, thanks to ICTP, through their donation of Arduino tiny machine learning kits, and this has motivated us even to do this research and other form of research. Now, this is the architecture of the data collection with sensors. We have 2 types of sensors: the TinyML Arduino Nano BLE Sense, as well as mobile phone. Data were collected with Arduino Nano BLE Sense and deployed on Edge Impulse. But because we also have the intention of deploying our mobile phone, our model on mobile phone, we decided to collect data sets with our mobile phone, and it is also deployed on the Edge Impulse. Now, the Edge Impulse has a section where some of these signals can be sampled. We found out that in collecting these signals from the poultry farm, there are a lot of noise that comes with the data signals, and there's a need for us to be able to, remove this noise so that it doesn't hamper our model at the end of the day. So the sampling section helped us to sample the data set so that unwanted signals can be removed and we can have a fine-tuned data set at the end of the day. Now, the data set of these healthy and non-healthy features were being extracted from them, and the edge impulse helped in extracting these features using some of the algorithm present on the dataset, like MEL FCC, and this is being shown in this where we have the sample, the features that has been extracted. What next? We intend to extend this dataset collection through on other species of poultry birds, such as layers and noilers, because we found out that these are common poultry birds farmers in this region keep. We have the broilers, the layers, and the noilers. And the data sets will cut across the several ages, day old, week old, month old. And these data sets are being collected in the morning, afternoon, and night to have a span of different time, as well as weather conditions are also being collected alongside with this audio data set in order to know what is the correlation between some of these signals and the weather condition. Also, due to the help of the experts, we'll be able to label it as healthy and non-healthy. Now, according to Chuan, which says, tell me and I forget, teach me and I may remember, involve me and I learn. We intend taking back this idea, this model, as well as the mobile system back to the farmer, because we believe if we involve them, they will be able to learn better. And taking back this, our research, we plan also for them to be able to learn. Expected outcome. The research is expected to gather data sets of acoustic-related poultry disease, develop a smart model for poultry disease identification and classification for the purpose of mitigating loss on farm and for easy diagnostics. The approach is expected to be faster and seamless with a friendly platform. I want to thank my team for this. We have machine learning experts, we have cloud computing experts, we have IoT experts, we have animal scientists on the team to be able to help us with the labeling of some of these data sets, as well as we intend taking it back to the farmers so that they can get involved. So we also have agricultural and rural extension specialists. Also, most of our students from engineering, some of our students from engineering and computer science are also on this team in gathering some of these data sets. Thank you.
That was really great. Thank you so much. I think there's yeah, do actual copy because I'm unmuted, so I can talk. There's a couple questions in the chat. I don't know, Segun, if you'd like to unmute and join, I can read some of them out if that's easier for you as well, or you can just go through them. You let me know what's best for you.
That would be great. Reading it out for me will be better.
All right. So I think one of the first questions is, how do you know that the chicks are unhealthy? So how do you go about like labeling and collecting that data?
Well, we have animal specialist on the team who is also very vast with the clinical testing. So he's the one doing some of those testing and affirming after, physical and inspection. There are some clinical tests he's also doing to affirm some of those diseases and be able to label. So he has been helping with the labeling, basically.
Got it. And so there's sort of like a public, like you're doing a manual expertise to develop this sort of data set that then hopefully you could use to automate the testing in the future.
Yes, very well.
Yeah,
yes.
Got it. So a bunch of people got really excited as you were talking about data, and they were going, do you have any samples of the data? Is there any chance that the data would become public at some point? I think a lot of people are really excited about your data set that you're building.
Yes, that's what we are planning, that we'll have the data set on Kaggle or GitHub so that people can have access to it.
That's awesome. That sounds really exciting. I think given that there's like 5 or 6 questions about that popped up, there'll be a lot of people who'll be really excited. And then I guess one of the questions was, is the study still going on? And I think based on your future work, you're still going and hope to build on this for sure.
Yes.
Yeah. And then somebody was asking about how do you collect the sound from individual chickens and try to tell it apart from the whole flock if there's a lot of them in there.
Okay, so one of those things we are doing is identifying the sick ones and isolating them, then placing the sensors close to them to be able to collect those data. So basically, that's what we are doing now. But we are trying to look at doing it in a better way where we map the sensors on their body and get more data. But for now, we just identify them, isolate them, and collect the data.
That makes a lot of sense. Yeah, you gotta start somewhere and gotta get that initial data and get that initial model before you can build the full systems. Yeah, that makes a ton of sense. That makes a lot of sense. Cool. Let me see if there's any more questions that popped up. I think it's just data set. You really must have struck on a very popular topic because there are about 10 about the data set.
Yeah, it's a major issue, and we believe from this part of the region, if we can have access to very good data sets, we should be able to do better with machine learning modeling.
Yeah, and I think there's one last comment here that's saying the climate and that might impact your data set, and so they're curious about as you do more collection and research, the correlation there on, I think, like the weather conditions and how the noises are coming out and those sorts of things.
Yes, we are thinking so, and that's why we are expanding it for a whole year to cover the whole season, so that we'll be able to have a robust data set going through the whole season in this region.
Yeah, that makes a ton of sense. That's really awesome. I want to keep asking questions because I think this is really exciting, but I think I'm going to get in trouble with Marco if I don't start to move on towards the next one, because I think is it time or do we have extra time? Oh, I think we might have extra time. I'm looking at the schedule. I think I'm off by 10 minutes, so we might have extra time. So I guess given that, I had sort of a question for you, Segun. So if you're going to mount it on the individual birds, which will get you really good data, if you wanted to scale this to detection for, let's say there's just like a bunch of birds in one room, right? And you didn't have a lot of sensors and you maybe couldn't go in and mount all of them. Do you have any ideas about how you might be able to still be able to like identify which particular ones are sick or healthy?
That's a tough one.
Yeah.
I believe, well, that's why we're open to collaborations and assistance in ways to get it. That may be tough, but we've not thought of it, but it's a good one to think about.
Yeah, no, I don't know if that's even possible. I was just like, ooh, how would you take this model that you made and like infinitely scale it, which is challenging. But maybe that's what, maybe that's your $1 million startup idea. So maybe we shouldn't, reveal your secrets, and then you can, sell your device to all of the poultry industry worldwide.
Yeah.
So if I may add, one kind of general question. So where do you plan to share this data? Because that's something we have been discussing in our network, right? So as Brian said, that's really, I mean, given the number of comments, many people are interested in this sort of data. I had a meeting this morning with colleagues from Tanzania, where they have this AI 4D center in Dodoma. And they were raising the same issue, right? Getting local data so that then you can work on interesting models. So one kind of general question is, where do you share the data? Segun, what's your take on that?
Yes, GitHub is one of the places, and Cargo. And since we want to cover it for a whole year, we are looking by November or December, we should be able to post our data set on Cargo and GitHub.
And then you will let us know on Discord that the data set is available, right?
Definitely, definitely.
One last comment, Marco and Segun. One thing that I liked about your project, also when you collect the data, as you said, you also use a cell phone. People is a little bit worried sometimes to mix it, let's say, different sensors. But in my experience, having a digital microphone from Arduino Nano, for example, and a digital microphone from the cell phone, when you do the same, let's say, 16 kilohertz sample rate with the 16 bits data, work very well. So you can, because it's easier to collect data with cell phone in several areas. In your experience, everything worked fine when you mixed both data?
Well, we've not, for now, since we are just collecting data, we are not sure. But we believe it should mix better, because when you are deploying storage on a mobile phone, you should be able to have a better performance. So that's why we are, looking at two different kinds of sensors and see what we'll have at the end of the day. It's more or less like a research to see if we will have a better performance at the end of the day. If not, then it's a contribution to knowledge.
Okay. Thanks.
Yeah, and I think oh look, somebody has a link for the open source foundation. Oh, maybe they host data too. Okay, cool.
Okay, I think that's a good one. So we could also consider that.
Yeah. And then I think one person was asking if you can share your contact details in the chat when we're done talking, because I think people want to talk to you about it. And I've gotten another direct message. Somebody else is looking for a collaboration in Poultry. So I would suggest that if you drop your email in the Zoom chat or onto Discord, it seems like there will be a couple of folks who might be reaching out to collaborate, which would be cool. Awesome. Does anybody else have any other questions they wanted to ask Segun right now? No, it just sounds like everybody is just waiting, very, very excited about your final data set. So, a big hand on this project. I think this is going to be really exciting. And I think with that, I'll toss it back to Marco to do the next presentation.
I'm making a presentation on leveraging TinyML for tracking Eidolon Helvum movement pattern and forage technique. And my name is Halleluyah Oluwatobi AWORINDE. I'm from Bowen University, Iwo, Osun State in Nigeria. Eidolon Helvum is near threatened, going by the global conservation status because of a significant decline in their population, and particularly in Africa. Eidolon Helvum have been found to be broadly distributed across lowland rainforest and savanna zones, from Senegal in the west to South Africa in the south and Ethiopia in the east. Going by the distribution of Eidolon Helvum, it covers an area of 14,510,000 kilometers square with a perimeter of 34,000 kilometers square and fragmentation index of 0.23. Majorly speaking, Eidolon, equally known as palm bat, are of two major species. The first one is the Madagascar fruit bat, and then the straw-colored fruit bat. In this research, we are focusing on the straw-colored fruit bat, which is equally known as Eidolon Helvum. And on my screen, you will discover that I placed a picture of the ventral view of a female bat, which was captured on Bowen University campus on the 22nd January 2019. And the bat actually has a wingspan of 66 centimeters and a weight of 250 grams. Most bats rest during the day, but forage from dusk till dawn. The bat population is a dominant feature on Iwo campus of Bowen University. And we've come to discover that some of the major characteristics of bats include ability for flight, gregarious social structures, longevity, and low fecundity. Bats cause discomfort to humans by their distressing noise, offensive odor, and pollution of the environment, especially with excrement. This might have contributed to the reason why human being generally doesn't have interest around this mammal, and they have a lot of misconception about them in terms of maybe they carry evil, they are bearer of evil reports or evil occurrence and the likes like that, especially in this part of the world. Straw-colored fruit bats are widely distributed throughout Nigeria, and they happen to be the second largest fruit bat species. They travel a cumulative distance of over 2,500 kilometers in about 5 months. For this research, we try to focus on describing the roosting pattern to notice maybe the presence or absence of bats and appraise the impact of roosting habits of straw-colored fruit bats on specific trees within Bowen University. Not just that, we try to map out roosting location of straw-colored fruit bats on Bowen University campus and then analyze their movement pattern as time progresses. This is the study area, just like I said. Bowen University campus is located in the southwestern part of Nigeria in a state known as Osun State and on a hill just outside the city of Iwo that has a population of 250,000 persons. This is the study area, and you will notice movement of bats in the cool of the day, and on the other video you notice the tree on which they are roosting in the university. These are some of the roosting locations that we try to map on Bowen campus, and we try to map no less than 20 locations on Bowen campus where we can find these bats roosting. This is the map layout of the bat roost on Bowen University campus. You can see them on the screen as they are. Then we try to follow the process of setting up the net to capture the bat. We capture the bats and then release them from the nets that we use in capturing them. Thereafter, we try to measure the weight of the bat. Not just the weight of the bat, we measure the wing as well, and thereafter we tag the bats before releasing them to the wild. This is a description of the tagging material that we used. We use a GSM GPRS device, which of particular interest has a stand time of 12 days and a working time of just 4 to 6 days. This gives an insight to the limitation of the tagging device that we have used so far. And these are some of the sample data sets that we have gotten so far. One of the major interests in this is that we ensure that the mass of the tag that we use does not exceed 5% of the bat size for easy movement and flight, and for longer journey as it progresses. And this is the other sample data set that shows a description of the time that they were tagged and the time they took off and the distance they cover over a period of time. In terms of variability of data set, this gives information about the general body mass of the bats that were tagged and the variation across gender. You will discover that we're able to capture more male gender than female gender bats, and then the tagging percentage is equally displayed on the screen. From our observation in terms of the movement pattern and of particular interest on Lakashegbe Shere, we discovered that it took off from Bowen campus on Saturday night after it has been tagged and moved a distance of 5 kilometers between Saturday night and Sunday morning. Then from Sunday till Monday, it has moved more than 30 kilometers within a space of a day. And you can see the movement pattern, the directions that it went from. It moved from Iwo in Osun State down to Oyo State and is heading towards Kwara State. And other observations we could infer is that for most of the bats that were tagged, they don't all go the same forage location, despite the fact that they are taking off from the same roosting site. And some of the bats did not leave their roosting location for other places till the tag went out of power or reach. Another observation we discovered is that female bat tends to travel further than male bat, possibly in search of food for survival. And this is the process or the lab work that we did in tagging and measuring the bats before we release them to the wild. And you can see the video in the course of releasing the bats, the process after it has been tagged for us to have it take to flight. Now the bat is taken to flight, and then we are taking reading of the location and its movements as it progresses. Then what is the new research direction that we are looking at? We want to leverage TinyML for more insight and data, especially in terms of exploring the possibility of TinyML for lighter tagging and longer tracking time. Our wish is to ensure that we go far less than 5% tagging size of the bats, and to ascertain if and when these bats return to their roosting site. And with TinyML tags, we hope that several sensors embedded in just a single tag, such as accelerometer, gyroscope, audio, cameras, and the likes, can be used to gain more insight about this mammal. With TinyML, a low-power resource tracking is achievable, and thereafter we intend to publish the data set gotten when we have populated it the more. These are the research team members. We have a conservation ecologist, we have an electronics and communication engineer on the team, we have a computer scientist, and we have a wildlife biologist. It is very important for me to acknowledge the support we received from Data Science Africa that gave us a grant to the tune of $10,000 for the project, and we cannot but appreciate our university, Bowen University, for providing an enabling environment to get the work done. We are still open to collaboration and further support on the research. Thank you. These are some of the references.
Great work there too. Looks like there's a lot of really exciting data sets that we're all going to get in open source. And I think this is actually a really important point because machine learning in general seemed to kind of only take off once there were a bunch of large open source data sets on really interesting topics. And if you think back to around 2010, I think it was 2010, when the ImageNet challenge came out, that was sort of the first big image machine learning challenge, and a bunch of researchers took this wonderful data set that some other researchers took a long time to develop, and then started producing all these neural networks and all these exciting things. And so I think it's really exciting that we're actually starting to get to the point where there's enough folks working in this space that we're getting some real targeted, interesting data sets to work on. So that's really, really exciting. So is our speaker, yes, here. Okay, great. So you can unmute. I guess I will start reading some of these questions as well. So I think the first couple of questions are all around the sensor. So I don't know if you could talk a little more around the size and form factor of like the original tracker versus the one that you're developing now with TinyML, and how you're trying to think about the changes in the design there.
Well, when I comment before he starts to answer, I think I love this kind of a project, because I think it's a real type of research that you can move to TinyML, because when you go to there, you have a longer time with the battery. You can have more sensors, as Halleluyah said. So very good. It's good. It's bad your sign.
Hello, can you hear me now?
Yes, yes.
Oh, yes.
Oh,
Yes,
thank you.
good.
Yeah, sorry, I was having network glitch from my end. That's the reason for it. Yeah, thank you for giving me the opportunity to make a presentation at this workshop. Yeah, that's just part of the work we are doing. It's actually a work in progress. And that's why we had to make presentation, to gain more insights from colleagues here and senior colleagues accordingly. Yeah, as regards the tag, we try to, at the moment, we try to make use of GPS, GSM, GPRS tag on the bat. And one of the major area of interest, because of the flights and ability to travel far, we ensure that the size of the tag does not exceed 5% of the body mass of the bat. That was one of the particular areas of interest of our research, that for us to allow the bat to take to flight easily and for us to be able to take more readings, we ensure that the tag is as light as possible after a lot of options. And one of the area, if you check some of the pictorial presentation, we ensure that the size of the body mass does not, the size of the tag used on the bat does not exceed 5%. The moment it exceeds it, we try to drop it down. And some of the contributing factor to it is that, we had to use like light thread to tag the bat together with the tag. And at times, maybe in the course of adjusting the tag and the thread, it may increase in size and go beyond 5%. At such point, we try to adjust and ensure that we use lighter pegs or lighter thread in tagging the bats. So majorly speaking, we didn't allow it to exceed 5%, and in order not to injure the bats. So these are some of the things that we put into consideration. And beyond that, as regards the average time it takes to track, that's one of the area of challenge that we are having at the moment. And that's why we had to bring this up to gain more insights. Most of the time that we tag these bats, the tracking time doesn't go beyond 2-3 days. For instance, if we tag them on Saturday afternoon, we may not be able to track the bat beyond Monday morning. And we feel that's why we need TinyML devices to help in longer tracking time, at least with low-powered resources, to help in tracking for a longer period of time and to better understand the pattern of movements of this bat. So those are the major things that are of challenge to us at the moment, especially in terms of power consumption and other things. Thank you.
A comment. I think that your project is very good tied, for example, what Seed Studio is trying to do. Their devices are very, very small. It's very, very light. They have a battery control inside. So you can have a very, very small device. Maybe it's with, of course, connecting outside the GPS. So maybe it's a place for you to look for.
All right, thank you for that. So we'll look into that.
It also looks like Dipesh from posted in the chat that they had worked on energy harvesting architectures before and posted a link to a paper that might be helpful and useful to keep your battery life going while you're flying in the chat. So you should take a look at that. That could be really cool. And I guess actually I had a question for Marco for you, which is, IoT communication here, right? So I think GPS and GSM is pretty battery intensive. I'm wondering, and I guess I don't know the range, and this is out of my communication expertise, but is there a different protocol that could be used that might be more energy efficient and help in that way?
Yeah, sure, definitely. I mean, I think it all depends on how precise should be location be, right? If you're happy with, a device that lives for long, but without, very accurate position, then you can look at other technology. I will post a paper from Diego, which is is here, right? Diego Mendes, and he worked on some, I will make him co-host so he can comment on that, on some TinyML-based localization techniques. So that was for indoor localization, but I wonder if you could use the same for, outdoor as well.
Hey, yeah, we used basically fingerprinting. So try to collect different information on RSSI. I mean, the values of power received by different sources. And then with that, we try to understand or try to learn where this device is. And the first approach was based on classification, and now we're trying to move it to regression. And that's, yeah, I mean, you can actually contact me if you you want to work on this, or if you want to know how we did it and apply it to your project.
All right, thank you.
Thank you.
Cool. A bunch of other questions have popped up. Hold on, let me try to make sure. I think there's a couple of questions around sort of along this communication line in terms of weather and network instability. You know, if you found that as they're going over large distances, if that also started to impact your ability to track them, even if you had battery life.
Actually, on the issue of coverage, we factored that in the selection of the network that we chose. We ensure that is the network with the largest coverage that can actually go a long distance. But you know, for now, we cannot track beyond 3 days. So we can't really say maybe the rate of stability or instability of the network coverage. But one of the things that we factored or put into consideration is that we ensured that we made use of a mobile communication option that has the largest coverage.
That makes a lot of sense. Yeah. Yeah, it's very challenging, right? You want the most coverage, you want to go long distance, but you want it to be low power, and you want it to be reliable and accurate. We need everything. Yeah, but I mean, maybe there are interesting ways to do it. You know, I've seen, I think from a lot of the wildlife tracking stuff that I found that I've seen coming for like elephant tracking, they've done a lot of things where if you can reduce the amount of times you send back data and send, you know, smaller packets of summary data, like they were doing a bunch of machine learning to detect, say, like a gunshot, so they're not sending back real audio, they're just sending out sort of like pings. Something like that really helped. I know you're trying to actually track location, so that might not totally be one-to-one, but maybe there are ways to, you know, sort of compress the information into summary signals, and maybe that helps with reducing the amount of times you have to turn on the radio.
All right. Thank you.
Yeah. But I would go bother Marco and Diego. They've done actual more networking stuff.
I actually have a question if I
Yeah, go for it.
I can. Just a short question. I mean, do you have any kind of a study to understand how this device on top of the bat is actually affecting the normal behavior of the animal? Because I mean, it's different when you have elephants. You know, it's that device is nothing for an elephant, but for a bat, I don't know if you have some kind of a study to compare.
None for now, but it's a direction that we can actually look at to see maybe their reaction towards the tags, and maybe if there are. But we try to ensure maximum safety for the wild in the course of tagging, so that none of them goes bad. Yeah.
Okay, thank you.
Does anybody else have any questions? Oh, there comes one. The question was, what kind of battery are you using?
Yeah, we use, just like in the description that we have on the slide, we use lithium, all these LiON battery. So that's the type of battery that we use.
And Marco, it looks like there's one person with their hand up that wants to ask one more question.
Yeah, you can unmute yourself, Andrew.
Thanks, guys. Can you, I guess, how do these batteries, or how do these devices compare to cell phone devices? Like, are they analogous kind of chips, or is the size the same? Is the range the same? Like, how does the tracking on like a, you know, tiny embedded device compare to sort of like a cell phone device? Do you know? Does anybody know?
No, they're actually very small tags. They are not up to the size of a mobile device at all. They are just like maybe less than the size of a palm, and is majorly insignificant on the size of the bat. So it's quite small, just like a compartment that can take care of a very small battery and a SIM card. Very small in size. Yeah.
Okay, cool. Thank you.
I think though, to answer sort of a little bit of your broader question, like sometimes some of these devices literally are very much like we took a phone and we stripped out all the components except for exactly what we needed. And now we have a new device that we can use. And in some cases, it's a bit more like we've actually fabricated a custom board to try to make sure that we can go even smaller than that, or pack in new features that you wouldn't have on a phone, but you might need in this case, and all those sorts of things. So I think it's sort of an open question as to exactly the right way to do this. I think, Marco, we might be at time, but I feel like there's like 2 more questions, and maybe I can just grab one of them really fast and then we'll move on. One of them was wondering if there's any data about power consumption to understand the voltage drop. And another one was asking if you found that while they are flying very far, if they stop in very specific places.
Yeah, we get to take record of their stop at different points, and we look at the range of time they stop over before taking their movement further from where they are. So that actually is captured in our data sets, at least the time they have as stopover before moving to another destination and going on, at least for the range of 3-4 days that we have been able to track so far.
Awesome. Well, thank you so much for the really exciting presentation. And again, lots of follow-up questions. And yeah, everyone, get in the Discord, keep chatting. I feel like there's a bunch of budding collaborations here, and we should do it.
Greetings, everyone. My name is Ricardo, and I want to show you the project me and my colleague Luis are working on, a personal trainer powered by TinyML. Our objective is to find a way to integrate TinyML into the gym environment by creating a product that is small, battery-powered, wirelessly connected, and able to identify when an exercise is being done correctly or not. Our board of choice for this project was the Seed Studio Shell NRF52840 Sense, since it fits in all the requirements for its compact size, lower power consumption, ability to recharge the battery, built-in accelerometer and gyroscope, sensors that are essential for this project, a Bluetooth 5.0 antenna, and a microcontroller that can handle TinyML models. However, we needed a way to place the board on the side of a dumbbell. We came up with a 3D printed casing that helped us with the placement while providing a secure, protective housing for the board and the battery. This way, it is possible to bring the microcontroller inside the gym, while having it protected for accidental drops on the ground and being able to operate without cables. Our main focus on this project will be to classify 3 different exercises: the biceps curl, the bench press, and the lateral raise, all of them done using dumbbells. This choice was based on these exercises working different types of muscles: the biceps, the chest area, and the shoulders. As you can see here, these are the correct ways to execute those exercises, all done by the gym instructor Clayton Nogueira. In all these exercises, a correct execution is defined by the main muscle doing most of the work, while minimizing the work done by the other unwanted muscles. For example, in the lateral raise, you want to mainly work with your shoulder while minimizing the work done with your trapezius muscle or with the lower back. With this setup in mind, we can collect data in a real environment to form a dataset. It all starts by sending a command from a smartphone to the microcontroller. The microcontroller then starts sending the collected data from the accelerometer and the gyroscope through the Bluetooth to the smartphone until the exercise is completed. The smartphone at the same time is receiving and storing all this data in either a CSV file or an online Google Sheet if internet connection is available. But How exactly is the smartphone sending commands? By using the MIT App Inventor, an Android app was developed to work as a bridge between the smartphone and the microcontroller. As you can see in this video, it searches for all available Bluetooth connections, and when the connection is established, a blue LED is activated on the board. The app will then show the sensor data of all the 3 axes of the accelerometer and the 3 axes of the gyroscope. As the Send Data button is pressed, all the data is stored in a file inside the smartphone. This image represents a file generated by the app. It has a name that was chosen inside the app, a header with the name of each sensor axis, and each row after that the collected data from the accelerometer plus the gyroscope, in a classic CSV style of file. We can also better visualize the data contained in the CSV files by using graphs. Take the biceps curl as an example. The z-axis of the gyroscope has a greater variation of degrees when compared to the x or y-axis, something unique to this exercise that will probably have a great impact in the feature extraction when developing a model. Talking about developing a model, all the data collected can be uploaded to the Edge Impulse website to develop a classification model. In this project, we have the ability to classify it in a binary way or in a multi-class way. What this means is, the binary way will output the exercise classification in either correct or incorrect classes, and the multi-class will output the classification in 4 classes, 1 for each exercise being done correctly, and 1 when any of the exercises are done incorrectly. In this project, we decided to use the multi-class model since it will provide a better feedback when making inferences. The DSP can be done by using either FFT or wavelets. It is important to note that in the binary model, the DSP done by wavelets had a better performance, but in the multi-class model, FFT and wavelets had almost the same performance. As this page shows, the performance obtained when training a model by using FFT and wavelets in the spectral analysis is mostly the same in the multi-class model. Something important to notice here is the great accuracy achieved in either case. And even though 80% accuracy is not ideal when performing a test using the testing dataset, it is good enough for now and means that there is room for improvement in our model. So, having the model complete and loaded on the board, we can begin making inferences. This diagram better represents how the inference result will be displayed. By receiving a command, the microcontroller starts analyzing data from the accelerometer and the gyroscope. After 8 seconds of exercise, it sends the result through Bluetooth to the smartphone. Displaying the information received by the smartphone can be done by using a simple app made in the MIT App Inventor that will show on the screen if the exercise was done correctly or not. On the video on the left, I execute the exercise in the correct way, displaying a thumbs up on the app when the inference is complete. On the right, I execute in an incorrect way by swaying my upper arm instead of having it fixed on the side of my body, displaying a thumbs down on the app when the inference is complete. We want to express our gratitude to CNPq for sponsoring our projects and ideas, and Seed Studio for providing us with the development boards used in this project, and also everyone who has helped us somehow along the way. We hope that our product will help people achieve better results in their workouts and motivate them to maintain a gym routine. If you have any questions, please ask them in the chat and I'll be happy to answer. Thank you.
Another great project. These are all so fun and so different.
Very good.
Very exciting. So if anyone has particular questions, they can put it in the chat. It looks like one just came in that said, how many sets of samples are needed for classification, like during inference? So how long do you need to sample during inference to get a good result? And then, yeah, we'll start with that one.
Oh, for now, we are capturing, I think it is 8 seconds of data when doing the inference. Yes. That is like, I think 4 or 5 repetitions of an exercise.
Cool. Yeah, I think the other one was around is your data set available? Will it be available? I think that's the theme of the morning, or afternoon, or evening, or night, depending on what time zone you're in.
For now, it isn't available, but I think in the future it probably will be. We'll be uploading it on either on Kaggle or another website.
Yeah, I think this is the real question: is what is the right one? Because I feel like these TinyML data sets are like, they're small enough that you might be able to put it straight on GitHub, but they might be big enough that it doesn't exactly fit. Yeah, kind of funny.
Ricardo, I have a question. You didn't mention in your video about what model was used for you to do the classification when you're training.
Yes, we use the multi-class model, but our neural network was done by using the dense neural network, the DNN. I think someone asked, can the model count the reps done? Not yet, and I sincerely don't know if it will be able to count in the future.
I guess maybe you might need 2 different models, you know, like one to tell if it's like roughly the right motion, and another one to try to like look for, I don't know, I imagine like there's like a spike in the accelerometer, right? When you, well, depending on how you do the rep, but if you're the kind of person who goes up and then like short stop comes back down, you know, maybe you might get it, I don't know. I think there was also a question with somebody with it. I think Andrew Vivian might have had his hand up if you wanted to ask another question.
Oh yeah. So I had a question. It said in the presentation, you said that you have to be connected to the internet in order for the gyroscope to register information. Do the devices, if they're not connected to the internet, can you like store them on disk? Like, are the little devices? Do the little devices have enough disk space, or do you just have to add something extra? Did you do that, or does that not apply here?
But there is 2 ways to store the data. One is by saving in a CSV file on the smartphone that you're receiving the data through Bluetooth, and another is to send the data to an online Google Sheet if you have the internet connection. If you don't, you can safely store in the smartphone. No problem with that. You can also do both.
But this is during when you are collecting data for preparing for the training. So you do that because yes, during the inference, you only send the result, correct, to the smartphone to say it's correct or not correct.
Yes, exactly. When you're doing the inference, the data is being used by the microcontroller, and he only sends a result to the smartphone, like something like correct or wrong.
You you don't need to use the Wi-Fi for
No.
anything.
And in theory, you probably don't even use Bluetooth if you just wanted to have it like light up an LED that said green or red as well at that point.
Yes. Yes.
Yeah, good point. Yeah.
Thank you.
I think there's another question around the FFTs and wavelets and why you wanted to use that to pre-process your data and what that sort of meant.
FFTs are basically to divide our signals in frequencies, right? So that we could have a better visualization of what was happening. And the wavelets we were basically testing because it was a new thing in Edge Impulse. But for our model, they both had the same performance. So we decided to stick with the FFTs because we were working with them already in the past.
Yeah. I think this also brings up a broader point, which is that often many machine learning approaches will do some sort of pre-processing type thing, right? Where they'll take in the raw data and they'll apply something to it before they pass it to the model. And often what that can do is make the data easier for the model to learn from. And so that's often what these things are used for. It's just like sort of a broader point. And then just one last thing, because I've had a lot of people ask me sometimes, oh, my particular sensor, what's the right pre-processing to use? And my answer is, I don't necessarily know, but I guarantee you that if you look in the literature of non-machine learning, like people have been processing data for decades, and there's probably actually really good literature that says, hey, you have an audio signal, you should use these sorts of things. You have a visual signal, you should use these sorts of things. You have a time series signal, you should use these sorts of things. And often if you start with what's in the literature and then pass it to the machine learning model, it works a lot better.
Yes.
I think also, Ricardo, there's two more questions here, which are around, do you have to start it in a particular orientation, or can the model adjust for somebody starting in a bad place?
This is a question we had when developing this project, and it doesn't necessarily need to be in a certain orientation, because when we collected data, we took the care to spin the box so we could have in every single orientation. And to be fair, it doesn't really matter, because something like the biceps curl, it affects mostly the Z of the gyroscope, so the orientation doesn't matter in this case. I think there's an interesting question by Sharon, and that she asks, what triggers the onset of classification? For now, it is running all the time because we're still in this part of the project. But in the future, we are trying to adapt something like a way to wake from the deep sleep on the microcontroller so that it can start by collecting the data and inferencing.
Oh, that'd be really cool. And probably means you could leave it on the equipment for days, weeks, months, years.
And it could do something like pressing a button on the smartphone as well to start collecting or inferencing the data.
I have a question. I think that you don't made real technical measurements, but you feel about the battery. I mean, when you have a full charged battery, take longer days, weeks to have an idea about that to using the equipment.
Yes, since it's running all the time right now, the battery lasts almost 36 hours, and we are running a 330 milliamps battery. And I think, if we can implement this deep sleep correctly, it will work for weeks.
Yeah, okay.
I think there's probably time for one more question. So it looks like there's a question about real-time data transfer. They've mentioned a couple of different sort of technologies, wondering like how real-time you can get the data transfer. And then I think the other one that may be interesting is, why'd you place the sensor on the equipment and not on the human?
Yes, about the real-time question, I cannot answer your question because I never used something like that. But what I can say is that the objective was to have something reliable and easy to set up when having on hand, not necessarily needing to use the internet or something like that.
It's important that this is a embedded machine learning project. So everything should be inside the device. That's because Bluetooth was used, as he said, because it's a very small amount of energy is necessary to send the Bluetooth to the cellular phone to receive the final inference. And also, as Brian said, even if you don't want to use the cell phone, you can change the color of a LED in the device to see if it's correct or incorrect the exercise. You don't need any kind of communication. Of course, it's more the communication used during the collect of the data before the training is more intensive. But I think that, as Ricardo said, they use the Bluetooth and worked very well to collect it. The data is only, you should do this only once, let's say, or before the training. No, it's not something that you should transmitting every time.
I think we sort of are out of time, so we should, Marco, move to the next one. But I think Marco made a good point, which is you could also use sound to communicate the result. You could have it just like beep at you angrily if you do something wrong. So thank you, Ricardo.
Hello, everyone. Today, I'm going to be presenting our work done using TinyML. It was presented as a paper at IEEE Systems Conference in Vancouver. So the title of the paper was Sleep Apnea Detection System Using Machine Learning on Resource-Constrained Devices. I am Neena, GOVEAS, who is making the presentation. I will go through briefly the motivation for doing this work, some core concepts, our proposed solution, results, conclusions, and references. The motivation for this work was based on the fact that in a disease or a condition called as sleep apnea, the upper airway gets blocked and there is difficulty in breathing. Now, this results in several issues to the person, and a typical way of having such a condition measured is by using something called as overnight polysomnography, which involves going to a sleep lab and working with some doctors and other technicians, and a large team is required. You can understand that going to such a setting may or may not be the ideal way to detect it. Okay, so our motivation was, can we use machine learning on maybe low-cost microcontrollers and still do the job that should have been done using a formal sleep lab kind of a system. The additional benefits, of course, are this is a low power consumption system, and we could probably have very low latency, could be done in the patient's home itself, home conditions itself. Okay. Now, the way it is done is that you look at the ECG signals which are generated and check for any indicators of sleep apnea. There have been studies using ECG line. For example, Wang et al. Has presented a single line ECG, which can be used to detect sleep apnea. Kincha et al. Has used Raspberry Pi based support vector machine based system, which also could successfully detect sleep apnea. What we are looking at as part of this presentation is to see whether we can do it with something even more cheaper, and can we use TinyML for the actual detection. So the ideal solution would be very cheap, so everybody can afford it. It has to be real time as far as possible. Possible actuation can be done, because not only should we be able to detect it, but maybe in the future you could do some actuation such that the person comes out of this phase. It needs to be compact, because the person has to be able to wear it and sleep. And it should work in situations where there is no internet connectivity. Right? Now, of course, we are looking at TinyML. We knew that the possibilities of using TinyML and doing many things is very good. So what we actually decided was to look at something which will actually work on the device itself, low latency, there is no need for transfer to the cloud or anywhere else. So data privacy is there. And we've tried to use the most cost-effective microcontrollers possible. So for our system, we decided to try using a Raspberry Pi Pico. It's around $8 US, ESP32 around $6 US. Of course, things would be working on Arduino Nano, BLE Sense, etc. And we use the Edge Impulse platform for training and deploying the models. Edge Impulse platform helps us to put on many other devices also. Since we had access to this, we decided to try on this. Okay. So our complete proposed solution was you had ECG signals which can be measured using an AD8232. ECG time series are segmented into 3-minute durations. The features are then extracted from these 3-minute duration signals and they have to be processed within that period. So essentially the proposed solution pipeline is you start with the ECG signals which are being captured. They are segmented into 3-minute intervals. Roughly around 200 RR intervals are obtained. We used two possible models. One which is model A, which was looking only at RR intervals for training. The second model B was using several other features which are extracted from the RR intervals, mean, standard deviation, and NN50 measures. And they were used to classify ECG signals into apneatic or normal. Okay. Since we had no access to an actual sleep apnea patient, the capturing was done using a normal person's ECG. But what we did was we tried to put in the MIT VIH sleep apnea dataset and tried to do the apneatic part. Okay. The data processing block took the neural network, converted it into a single C++ library, which was further optimized by the EON compiler tool of Edge Impulse, causing even lesser RAM usage requirement. What we found was for model A, using only RR intervals, we required only 4.5K and flash usage around 215.8K. And for model B, the RAM usage was 3.2K and the flash usage was 79.9K. So the main question was, can these devices handle the computation within the time limits? Yes, we found that they could successfully be done. And why did we use C++ libraries? Because they do not have any external dependency and they can be built using any C++11 compiler. And the model can be deployed onto any device as long as it has sufficient computational power. So these are some of our results. We found that validation as well as test accuracy was quite good. And then we got precision recall and F1 score, which were also quite suitable for such a device. What we found was, one of the critical things that we had to look at was that how much time does it actually take to do the signal processing, the classification, and overall total. And what we found was, for a comparison between ESP32 and Raspberry Pi Pico, both of them did well within time for both the models. And the signal processing was taking a little more time, classification was less, but successfully it could actually do what we are asking it to do. And this can be successfully used for detecting sleep apnea in patients using their ECG signals. Okay, so we can conclude that resource-constrained devices like ESP32, Raspberry Pi Pico, which are fairly low cost, they do not require internet connectivity, and within a few milliseconds, they can be used to detect sleep apnea. What we feel is in the future, we can potentially deploy this on even other devices, maybe customized devices, and it can be used to detect other anomalies also. And basically, we can work with any time series data. These are some of the references that we have used. More details will be in the GitHub page. Thank you.
Great work. That's super exciting. I'm wondering when your startup is coming out that has commercialized this technology and replaced all the sleep apnea machines in the world.
Yeah, but because it is a medical device, there are several steps which are required before I can get into it. But one of the reasons for starting this work was when I discussed with a doctor. The doctor knew several patients who were having this problem, especially elderly. But none of them had ever gone near a sleep lab and gotten themselves tested. That seemed like a very sad thing to do because it does lead to complications. And usually we ignore it saying they are old, which is not a correct thing to do. So I'm hoping at some point we will be able to make this device small, even smaller, because it should be convenient to wear. It's not like something, because you have to wear it while sleeping and it's not convenient for somebody, they will not use it. Yeah, the paper will be in IEEE SysCon 23. It should be available on the website. I will paste it, I will put the link on the Discord server when it is available.
Awesome. It looks like there's a question. How did you collect the initial data for training the model?
No, the data set was already present. So this is an MIT PhysioNet data set. There are other data sets also. Fortunately, when you're dealing with ECG, there are a large number of data sets which are well documented. And they're actual real data sets in the sense they were captured on patients. So they have all the problems that are associated with capturing on a real patient. They have not been cleaned. So it will have things like leads falling off. It will have things like people breathing, moving, other sort of artifacts which come in from a normal person. So we did have to put in things which would remove those as part of the pipeline. The choice of 3-minute interval was also decided based on how many good beats we'll get in each of the slots so that we can process it and get something meaningful out of it. Because if you make it too small, it will not be possible to extract anything meaningful. You make it too long, you might miss something, which is, if you're doing some averages, you miss things. So there was a bit of a, we had to play around with the timings. Sort of 3 minutes seemed a nice thing. So anybody working in ECG, it's a great blessing to have such good data sets. I mean, really
what kind of a sensor do you use for the ECG?
AD8232, and it's basically all the things that we used are available online in the sense that you can order from Amazon. So these are usual Arduino-based projects. If you see on ECG, what you get in that, what people use for those projects, it's the same thing that we bought. So there is nothing special that we used. It is the over-the-counter. I mean, in the sense you order from Amazon or one of those electronic stores online. That's it. Like we said, if we can make it with this, it makes sense. Anybody should be able to assemble it, put in our code inside it, and start the work.
So your secret sauce is your data, is your software on top of all
but
that.
we would, I mean, we are still in the process of trying to get some volunteers to do the sleep apneatic part so that we can confirm, because using a data set still is a data set. Like we need to capture the actual sleep apneatic part and ensure that it works. We want to have a few models, one of which is completely self-contained. It will just give a beep or something. Another one could be maybe send it to a local device, laptop or a mobile phone, so that the caregiver can get up and check whether it's working. And the third one would be sending it to the cloud. We are trying Google Health. I think they have started some way of putting data there and sharing with doctors. So let's hope that all these things work out, and maybe then anybody should be able to assemble it. That is the final goal.
It looks like there are a couple of folks with their hands up. I was wondering, Ramasamy, if you wanted to ask your question.
Hello, am I audible?
Yes.
Yeah, first of all, thanks to Neena for a nice presentation, and that too on medical side. It's a great work, fantastic. So my question is like, you are using ECG, this one, sensor with the AD8232. So my first question is like, can you use any kind of breath sensor to put up on the nose tip, which will help you? This is my first question. And the second question is like, basically the AD8232 is going to do a DSP extraction because they will be using some operational amplifier to do some filtering and all this one to get the PQRS peak and everything. So instead of that one, directly can we take the ECG probes and connect it to this one and use the DSP plots available in Nano or something, all the DSP ESG Pulse platform, we have got all the DSP plots, whether that will help. These are my two questions. Thank you.
Ideally, we should be doing something like that, where you directly can connect it to the Arduino itself if it has those possibilities. We did not explore it mainly because we wanted to use existing everything existing, in the sense that I should be able to order from Amazon. I should be able to put in the code for ECG measurement, which is available. People have been using it. We didn't want to disturb that part. Only change we wanted was, can the TinyML model also run along with doing all these things within the time frame? That was only change we wanted to make. Because if we made changes in everything, then it would still, it will be like, I made a customized device. There is no customization other than the model that has been put in. That's it. Anybody can make this ECG device. It is available. I think even school children can make this. Only change I will make is to put this model in, and it will give me with some LED glowing or something, or some mechanism that there is apnea or no apnea. That's it. So our aim was to make minimal changes from existing things. Of course, if it is being made commercially, they will have their own boards, they will have their own ways of capturing. We use breadboards, which is obviously not the correct way to do things. They will have their own, whatever, properly manufactured boards and things like that. So there is always things which we can do to take it far from what anybody can do. But our aim was always that everybody should be able to download my model, put it inside something they buy from Amazon. It should work.
Awesome. I feel like breadboards are a wonderful way to prototype things. So I'm all for breadboards. There was one other question. Oh.
If somebody's sleeping with your breadboard on their chest,
it's
not going to work. I will have to protect it with a plastic box. I'll have to put in all kinds of things, tell the person not to turn like this, turn like that. I can imagine the discomfort and reluctance to use it. So we are looking for at least putting it on a proper etched board, so that minimum amount of constraints are put on a patient.
Yeah, no, that makes total sense. I think there was one more question in the chat, and then I think there's one more hand up. The question in the chat was, how are you able to have a model that used so little memory?
That is the miracle of TinyML. That was the first part. If I get it to be very small, I should be able to use a $4 thing. If not, I'm stuck with whatever the larger device, which is more expensive. I want to make it as cheap as possible, so that nobody should feel the pinch of setting this up using it.
And then I think Andrew Vivian has his hand up again. So go for it, Andrew.
This is really cool. And one question I was wondering about is, I think I may have missed the sort of training pipeline, but so the sample data came from MIT, and were you training individual specific, individual people specific data on individual devices? No? Okay.
No, it's a general data set. So we made a bunch of apneatic, non-apneatic sets that we wanted of 3-minute duration, trained it, the model is trained. Once it is trained, we put it on the device and give it test data, and we check whether it is detecting it correctly. And that is how we did it. So the only problem was the device could not be put on a person who has sleep apnea to get the actual test data. That would be the correct solution. But for a normal patient, obviously we checked, and that is fine, working fine. But this the part of putting it on a sleep apneatic patient, we wanted to wait till everything is ready, because it's not correct to impose on somebody a device, and we put in all kinds of safeguards so that in one night we get as much data and everything, so that we can not trouble them again. So we are waiting for that complete solution to be ready so that we can propose it Awesome. But the doctor is definitely excited. He's saying none of my patients go to the actual gold standard treatment. Nobody will go. So we are hoping that some of them will agree to this, and let's see how things go.
Well, I wish you the best of luck with that. I think we're out of time. This is really exciting and really great work. So and I really hope you take over the industry and make it a lot easier for folks. I'll pass it back over to Marco for the next one. But I just also wanted to say one quick thing, which was on like quote the magic of TinyML. I think these sort of projects are showing that if you have a more constrained problem and you want to solve a specific thing with a machine learning model versus generating the large language model that can answer any question of anything, it really is possible to use a data set and work with a smaller model and be able to get that to actually be pretty accurate, which I think is what's really exciting and powerful about TinyML in general. And these tools like Edge Impulse and, as we mentioned, the EON tuner will help you make it and tune it and make it nice and good for your use case. All right, over to you, Mark.
Good day, everyone, and thank you for having me. I'll be walking through my presentation on rainfall estimation using audio monitoring and TinyML. So this slide shows the stages of the project and the approach we have followed. So we started by identifying what problem we are trying to solve, and then we did a literature review to understand the approaches that have been used, and then we adopted a methodology based on the survey, and then I will be also showing the results we've gotten, and then we'll conclude and show the future steps in this research. So problem description. So the problem we're trying to solve here is we're trying to replace the manual rain gauge. If you look at tipping buckets on the right, it measures rainfall by measuring the time it takes for the tipping bucket to tip over. And so because of this manual movement of the constant tipping over of the bucket, typically the rain gauge becomes difficult to maintain, and due to dead particles and other interferences, it's usually not efficient, particularly in measuring low intensity of rain and very high intensities of rain. Looking at deploying this tipping bucket rain gauge for Africa, it's expensive also, and it also requires skilled labor, because you typically require a human operator to constantly go and readjust the rain gauge. And based on the survey that we've also done on people that research that have tried to use audio data to capture the intensities of rainfall, typically most researchers formulate the problem as a classification problem rather than a regression problem. So the systems are only able to tell whether it's high rainfall or low rainfall, but we don't get the specific intensities of rainfall, which is required to replace a manual type rain gauge like this. So this is a chart of the distribution of weather stations across the globe. And if you look at the continent of Africa, you will see that the weather stations are very sparse. And apart from that, the weather stations, the green type, the green spot you see on Africa, the manual type weather station. So which means that in some form it requires a human operator to go and use it, which is what causes the lack of scalability of such solution. So the objective of this project is to investigate the relationship between the power of audio signals of rainfall and the intensity of the rainfall, both from real data collected and from simulation. and then also to use machine learning model to analyze the audio recordings, and then also investigate the deployment of the model on tiny controllers. So we started off by collecting the actual data in Kogi State in Nigeria. We collected data over 12 days in September of 2020, and we collected rain within intensities of 0.1 to 0.6 to 6.6 millimeters of rainfall per 5 minutes, and we have a total of 1,594 5 seconds chunks. So this is exactly the methodology. After we collected the data, which I just mentioned about, a total of 7,800 seconds is the duration we have over the 12-day period. We pre-process the data to extract the features, in our case, the average energy. Then we did data scaling, then do the modeling and the hyperparameter tuning of the model, and reporting also the energy consumption of the model. So these some example samples from the data set we've collected. At the top left is a time plot of the amplitude of the signal for intensity of 0.08, and then to the right is for intensity of 6.6. So as you can see clearly that for the high intensity of 6.6, the amplitude of the signal is generally very high during the 5-second period. And if you also look at the power spectrogram plot for these two samples, you will see that for the high intensity of rainfall, there's still high power, even at higher frequencies compared to the lower intensity signal. So from this figure, we from the analysis we have done both on the time domain and in the frequency domain, we decided to extract out the average energy of the signal. That's using a window of 1024 samples. So we'll move over the signal and take 1024 samples and average them and move like that throughout the whole signal. So we use this as a feature to train a support vector regression model and a deep neural model, and we compare this with using the spectrograms, which is just transform the audio problem into an image problem. And we discovered that just by considering only the average energy of a signal, we're able to get a mean absolute percentage error. Since it's a regression problem of 48.53%, which is much smaller than using the CNN. And just to point out, all the models we used, they are models that we tried out 40 kilobytes and less in order to be able to fit into our microcontroller, which is the Arduino Nano Sense board. So this figure here just basically shows the architectures of the model we're trying out. Then for the deep neural regression model with the best performance, it shows the plot of the training and validation, MAPE, and the number of epochs. And as you can see, just as we reported, the performance of the model was around 48%. So, and also this figure also shows that just by training for about 10 epochs is sufficient for the model, for the learning to saturate, so we don't have to go all the way to train the model. So which shows that there's a very close relationship between the average energy of the signal and the intensity of the rainfall. So this figure here shows the hardware setup. We have the Raspberry Pi, which is used as a data collection unit. We use the onboard microphone on the Arduino to record the intensity of the rainfall. We're also currently trying out different materials because we cover this box with different materials, aluminum sheets, and even plastic. We're trying out to see what material would give the best performance in terms of the audio sound quality needed to do the regression. And then we have a power supply unit there. And we also are comparing the data we've collected using a mobile phone and the data collected directly using the Arduino board. Okay, so in terms of the future work we're trying to do currently, so one is we've done some experiments currently using actual data we collected in Nigeria. Now we are also trying to carry out a simulation since raindrop arrival times can be modeled using a Poisson process, with each raindrop creating a transient audio pulse when it hits a resonant surface like the one we are using now. So we are trying to investigate if we use a Poisson process to model this rainfall for different intensities based on shorter arrival time. So we are making the assumption that with shorter arrival times, signals higher intensity of rainfall, and longer arrival times means that the rainfall is low intensity. So we are trying to compare using this simulation to the actual data to investigate exactly the relationship between the signal power of the rainfall and the intensity of the rainfall. Also, we plan to automate the data collection process. Currently, it's manual, and also to collect more data across the African continent in order to have more temporal and spatial information. Thank you so much for listening, and I'll be willing to take any questions.
Awesome work. Looks like the questions are already starting to come in. I think the first one was, how did you calculate energy from the waveform? And then how did you compare results with a TBRG sensor?
Thank you. We just calculated the energy just using the formula for energy in time domain, which is the sum of the squares of the amplitude. So we just use the window average energy. That's how we computed the average. Then I'm not sure of the other sensors compared with, but we hardly saw any papers that did a regression problem. So it was difficult for us to really compare.
Yeah, that makes a lot of sense. And Ramasamy, if you have any like links or stuff about what this other sensor is that you're talking about, maybe you could drop one in the chat or on Discord or send it directly, and then maybe there's room for future interesting work there. Who knows? Yeah, let's see if anybody has other questions they want to ask right there. Oh, I think Andrew has his hand up again. Go for it, Andrew.
This was pretty cool too. So I have a question. When you said you converted the audio to an image, essentially, I'm just wondering for the microphone. So does that mean the information was coming in and then you just took some snapshot and then like made it an image and then used X number of images over time to like, you know, do your classification?
Yes, thanks. That's a great question. So what we have done currently is we have not deployed our system on the field. So we collected the data and then we trained, and then we just tested by giving in 5 seconds sample. So the images are for 5 seconds chunk. So each spectrogram we computed was for 5 seconds. So you collect for 5. You have to have a sample of 5 seconds length before you can then compute the spectrogram.
Thank you.
Yeah, spectrograms are really, really cool and powerful because, you know, not only are you transferring from getting the frequency information on top of the time information, but yeah, you've now taken this audio slice and made an image, and we can use all the existing really strong image recognition pipelines that we have in machine learning then on that image.
If I may comment, really, really nice presentation. And are you aware about this ITU AI for Good competition that was around exactly this topic? So it was launched in blessed if you want to comment on that. It was launched last year, right? And it lasted a few months. So the goal was exactly to develop a rain sensor and a wind sensor in that case with no moving parts. So there were a number,
Yes, Marco, I remember I was part of the competition. I mentored. Okay. I remember you from that competition. That's the whole motivation. Yeah. Thanks.
Excellent. So now we're working on a second edition of that competition. So I hope you will be able to join, and I will post the link in the chat for people that don't know about it.
Yes, we are eagerly waiting to see what problem would come up for this year.
I think that's also just like a good note that ITU has been doing some really interesting TinyML challenges. And also if you check out TinyML Foundation, sometimes they run these sorts of events as well, which are really fun because they'll get prizes or community and whatnot around some of these activities. And so that hopefully will spur lots of more exciting projects and ideas. Does anybody else have any questions right now? Trying to look on the chat, make sure I didn't miss anything for any other. I guess I could just say one question is, do you think eventually that audio will be good enough to get a very accurate reading, or do you think you'll need to include other sorts of modalities of different kinds of sensors as well? So maybe I don't know, humidity.
I think this is the big, this is the big question to answer because, like you said, the error we have is still quite high. So I'm not sure what exactly is going to work, but we are trying out all options, and maybe we need to combine with other sensors. But for the audio side, we want to collect more data and see if just using audio would be good enough. Yeah,
I mean, the fact that it doesn't move is exciting. From it won't break.
Yeah.
I'm wondering. I'm just like thinking out loud if there are other sensors that don't move that could also help and do some of that kind of stuff too.
I have a question regarding the data collection. When you made the data collection, you gathered, I can say, try to get several different rains. You compare to get to after that to training as a regression. How you do that,
Yes, so each day that rain falls, we take out the device, record the intensity of the rain and save it across several days. Then we came and trained the model and tested. And that's the approach we followed.
So you had, for example, you capture the acoustic, and also you measure the correct the measurement. So you have several levels. You define specific levels, or you mean infinite, like analog levels?
No. What we did was, so we record for 2 minutes, and we have the rain gauge there. So for each 2 minutes that we record, we go and get the reading from the rain gauge.
Okay.
Yeah.
Awesome.
Thank you.
Let's see if there's any other last questions, although I guess we've got only 30 seconds before technically we're supposed to move to the next one. Anyway, I'm also going to tap out and promote Jeremy to hanging out with Marcelo, moderating the last couple of presentations. But I just wanted to say before I go more into the background that this is really awesome and really exciting. It's so great to see all these wonderful show and tell talks. I hope all of you join our talks when we start just the sort of monthly by monthly show and tells in the future. And I hope all of you submit in progress projects and ideas to those, because I think as we're seeing, there's a really lively conversation going on here, and there might be really great room for collaborations and growing the impact of TinyML globally. So this is really fun, and I love these.
Hello everyone. Good morning, good afternoon, good evening from everywhere around the world. So my name is Rehema MWAWADO. I'm an assistant lecturer at the Sokoine University of Agriculture in Tanzania. And today I'm going to present to you a topic on tiny machine learning on embedded devices. And throughout this presentation, I'll introduce a bit on tiny machine learning, then the motivation of doing this study, as well as a simple example so far of what we have done and our future work, because this is a work in progress. So I'll highlight also what is going to be done in the next course. So throughout the 3 days of the workshop, tiny machine learning has been introduced. And in brief, I can just say that tiny machine learning is the intersection of embedded devices and machine learning. And with tiny machine learning, with nowadays a lot of Internet of Things devices, they're connected. So tiny machine learning is really a very important research area, as well as an application area for these devices. Now, when you talk about tiny machine learning, we talk about constrained embedded devices. And what we mean by constrained embedded devices is that these devices are computing devices, and they are small in terms of computational power. They don't have that capability like a conventional computer or a GPU. And then also they are limited when it comes to memory. So, and these constrained embedded devices are found in everywhere. We have in home appliances such as smart TVs, smart refrigerators, in smartphones, wearable devices such as wearable watches, and also in systems of energy, example, renewable energy systems. So you can see that these devices are everywhere, and they need they're everywhere, and the more technology is improving, these devices keep on increasing. So we'll have so many devices that are connected. But these devices, again, as I said, they are constraints in terms of on-chip memory. They don't have enough memory as well as storage. So, and when you talk about tiny machine learning, we say it's an intersection of machine learning as well as embedded devices. Now, machine learning works on, like these neural networks need a lot of computational capabilities to do the training as well as inference. So when you talk about embedded devices, means that these machine learning models will not perform well when it comes to embedded devices, because they are limited when it comes to computational capabilities. So one practice that is normally done is that machine learning tasks are outsourced to the servers. These servers have higher computing capabilities, and then the embedded devices just does the inference. And this is what we have seen even in the past courses, or in the past 3 days of the workshop. Like most people have shown how inference is done in the embedded devices. So now, to address these challenges of memory constraints as well as computational, several researchers have done, it's a work in progress, and different research has been done to show that how you can develop lightweight models or lightweight protocols that can serve within these constrained embedded devices. And that's the motivation of doing this study. So another thing is that, being in Africa, I'm from Tanzania, so many studies have been done using IoTs, machine learning. But these studies, most of them require fast computational, like you require fast computers to do this training. So, and most of these, because deployment is pretty hard to in these devices, most of these models have just ended in the development stages, that the model is only developed, but deployment is not yet done. So, and again, with the model, when a model wants to constantly communicate to the cloud, it means that in some areas, like in most areas in Africa, are limited when it comes to network availability. So this becomes very impractical, especially when it comes to agriculture, because most of the small older farmers are located in the rural areas. And then within rural areas, the network is quite limited. So we need this technology of tiny machine learning to be able to do the inference and training on a device in a way that it can assist even an extension an extension officer to do when it comes maybe tasks such as pest detection or crop disease classification. So that's in a nutshell what this work is all about. So and within this tiny machine learning framework, we started experimenting with using the TensorFlow Lite. The TensorFlow Lite is a lightweight version of the TensorFlow, and TensorFlow is the machine learning framework that is used for many tasks such as image processing, and it's from Google. So one of the things that we started working with TensorFlow Lite, and we started testing this TensorFlow Lite when it comes to a mobile device. So, and again, TensorFlow Lite has two main components, being the interpreter as well as the converter. And what we have worked with that, we developed a model using TensorFlow. Then we converted it into a TensorFlow Lite model so that it can fit in an Android device. That's what we have done so far. So I'll demonstrate a bit of what we have done, and let me share my screen. So far, for the case of this presentation, I just ran on a few epochs. So this is a model that is developed using TensorFlow in Keras, and it's trained to identify or to classify 3 classes of tomato disease, one being tomato yellow leaf virus, another is a mosaic virus, and another, these are images of tomato leaves that are healthy. They don't have any disease, be it a virus or a bacterial disease. So it was trained, this is done also in the last classes, so model training and so on. So yeah, after that we saved, and then we, okay, so this, after training the model and getting all of the accuracies that we want, we saved the model in the file as a .h5 file. Now this is the file that is going to be converted into a TensorFlow Lite file so that it can be used in an Android device. So this is the code to implement how you do the conversion into a TensorFlow Lite model so that you can use it in the Android device. And after this, after converting it, we'll save it, and we're going to save it in .tf-lite. .tf-lite. This is the model version of the TensorFlow Lite version. Then after that, we started building an Android app. This is just a demonstration of a simple Android app that will works as follows. It's going to load an image, either loading it from the storage, the images that are stored in the device, or it's going to capture an image, and then it's going to tell us if it's either a healthy leaf, it's a tomato bacterial or leaf virus. So that's what this model is going to do. So apparently I did something to it. It's not going to demonstrate. So for those who would want this, I'm going to share this in my GitHub, and I'm going to share the code or demonstrate for you in the Discord channel. So just that was just in a nutshell what this app is doing. Just capturing either from the live capture or loading an image that is stored within the phone's memory. And yeah, I'll try to run it, but I tried it like last few hours, and it's not working for now. It's not bringing the output that we want. So I'll do it later, and for anyone who is interested, I'm going to share it with you. And let me come back to my slide. So what we want to do in the future, what we want to do with this, because this is just a work in progress and it's just in the early stages, we are going to use these employing the neural architecture as such, because in most studies like the ones that I've cited here, it has shown that how neural architecture such is a promising direction to go when you want to implement these models on embedded devices. So we'll experiment more with the neural architecture, such as well as incorporate memory efficient libraries that can be used also to optimize such models on embedded devices. That's what we're going to work in the future. So these are some of the references that I've included in this presentation. And thank you, asante sana. That's Swahili for thank you. So asanteni sana.
That was really good. It's so nice to see Jupyter notebooks and TensorFlow Lite and all the conversions. Marcelo, do you have anything to add with this?
No, I think it's a fantastic way. I think as she explained, because this is how TinyML will work. I think that what she had done so far is fantastic. You have collect the data set, create the TensorFlow Lite model. With that, it's possible to put in a smartphone. This is an edge machine learning example that works. And as she said, the next step will be to convert the TensorFlow Lite to TensorFlow Lite Micro to install in small devices, or for example, also using, for example, devices like with a little bit more memory, like the Portenta or the Nikla Vision, is possible, including using the model that she created with TensorFlow Lite. Is possible, for example, with the OpenMV IDE, to use that to install in that device, and the project will work as she have done. So very good, very good. I think this is the way.
I really like seeing the base information like you were mentioning. My background was TensorFlow JS, and then moving it on to an Arduino. You're doing the Jupyter Notebook route. Now, we're normally used to models on Edge Impulse. I'm curious about moving those models to Edge Impulse, or what are the positives of staying with the TensorFlow Lite method? Who am I asking the question to?
Oh, okay. Hello. Yeah. This is Rehema. Yeah. We are going to also do it in Edge Impulse. I've seen people doing with Edge Impulse here, and I think it's a good approach doing it also.
Yeah, exactly. Doing both ways gives you the full power to control what you're doing, whereas Edge Impulse has a lot of compression techniques to fit on the constrained devices. Do we have any questions in the chat? Not at the moment.
I would like to ask you, Rehema, regarding your cell phone application. What do you use? You use the Android Studio to develop your
Yeah. Yes. I used Android Studio to do the app development. Yeah.
Fantastic.
Yeah.
It's good. I think Andrew also has a question.
So yeah, no, this is pretty cool. So then you use Android Studio to deploy your application, but you were using TensorFlow Lite to train the models and everything. I think I'm getting a little confused on where Edge Impulse fits in. Can Edge Impulse be a like model registry where you can create your own sort of like models locally and then sort of like register them with Edge Impulse to kind of like be more automated / do more compression? Can you do that with Edge Impulse?
Okay, I haven't worked with Edge Impulse, but I think it can do that, because I've seen that it's easier way to do it with Edge Impulse, because it gives you all that compression and so on. You don't need to do a lot of like programming and all that in Android Studio. So I think Edge Impulse can do.
Okay. Yeah, in fact, what Edge Impulse does exactly what Rehema did in the Jupyter Notebook. you can enter with the image at the edge impulse, okay, and you can do some small treatment like a change to define the size of your image. After that, you can train, choose your model, do the training. The output of edge impulse, you can have both. You can have, for example, you can have the TensorFlow Lite model that you can download and use, and took this model and using Android Studio, you can create an application there. This is one possibility. Or you can also, let's say, download the model straight to your phone using your browser in your phone with the GS. So only for testing. So your model will work in that. Or you can go straight to deploy as we did in the couple of days before, and you shrink using a C++, for example, to have your model, and you can deploy in a small device with a camera. So there are things to do.
Okay, I'll take that. Yeah, that's nice. Thank you.
Any questions? Any hands up?
There is a question here, Jeremy. Fancy is interested to know if the data set was from Kaggle or she have collected the image in a farm.
Okay, this part of the project, we use the Kaggle dataset, but we have an ongoing project to collect data from the farm. And we're going to do several diseases. We even have greenhouses set up, inoculate, and inoculate, we can have a bigger dataset that will be available publicly.
Perfect. And there is another comment here, is about Sami. So great presentation. Yes, was a fantastic project. And he said in Cabo he hosted a decision competition. Very nice, very nice. So thanks very much. He put here the link. I think it's very interesting.
Okay, that's nice.
Yeah, and I must tell you one thing, Helen, that I like very much for you made a fantastic, let's say, short overview about what you have done from the last 3 days, and I think that was very good for people, because you did the result, a kind of a short view about what TinyML is, how to use, and show an application. So thanks very much for that.
Okay, thank you.
And good luck on your project. I think it's great the way you're tackling it.
Okay, thank you.
And people is asking for your notebook, so please put
I'll
your
share the
GitHub
notebook.
in the Discord. I think people can discuss with you in Discord. No, you can show
Yes.
including the results with some image about your phone.
Yes, I'll do that.
Thank you. Fantastic.
Good day, everyone. Today, we are gathering here to talk about a very interesting and relevant topic, word recognition using audio in Quechua. Who are we? We are graduate students from Escuela Superior Politécnica del Litoral, my college, Jonathan Santana, our tutor, engineer Ronald Criollo, and I, Karina Ortega. Have you ever wondered how many different languages are spoken all over the world? According to UNESCO, there are around 7,000 different languages on the planet. One of them is Ecuadorian Quechua, Quechua Runashimi, belongs to the Northern Quechua branch, that is Quechua 2. And to a greater or lesser extent, it is also spoken in other Andean countries such as Colombia, Peru, Bolivia, Chile, and Argentina. In Ecuador, it is spoken in 9 of the provinces of the Sierra and throughout the Amazon basin to the east of the Andes. Quechua has been implicitly and explicitly recognized as the predominant indigenous language of the country and has a great influence on the rest of the Amazonian language. So my question for you today is, did you know that there are indigenous languages in danger of extinction? Well, as we can observe on our map, the Ecuador region is marked, and it shows that there are languages that are endangered, seriously endangered, and critically endangered, according to UNESCO Atlas data. In fact, every year, around 26 languages disappear, according to the United Nations. This means that we are losing our linguistic and cultural diversity, and at an alarming rate. And this is because other languages are being adopted, since less than 35% of indigenous people speak a native language upon finishing school. Less than 5% speak their ethnic language upon finishing high school, and less than 2% express themselves in their own language upon completing university. Personal growth must also be inclusive and resilient. But now let's see with Jonathan the effort to preserve endangered language.
In India, for Khattari language, they developed a post-speech tagger in its built with the help of the hidden Markov model and the better algorithm of obtaining an accuracy of 86.84%. In the Italian, for Latin language, the objective was to classify 32 Latin phonemes. They perform a feature extraction approach experiment with 8 different training classifiers. The classifier obtained an accuracy of 86%. In Colombia, Cauca, for the Quechua language, they developed an educational mobile application of a technology proposal. Includes basic language concepts in communication, such as rating, color, animal, weather, etc. Next. In Ecuador, for the Quechua language, they developed a tool called Ticrachina that consists of web module and desktop application, and it for automatic translation from Ecuador Quechua to Spanish. SEAL International is an organization whose main purpose is to collect and disseminate documentation of the lesser-known language. Precisely on this platform, we found audio resources, such as documents explaining the teaching of the Quechua language of Salasaca in Ecuador. Next.
Therefore, the objective has been set that technology can be very useful in the preservation and promotion of these languages, which motivated the development of a word recognition model in Quechua, using audios to use it in voice recognition applications and alert system activation. The methodology used is as follows. First, collect audios in native Quechua. The SEAL organization authorized the use of this dataset, which contains short audio recordings of words recorded by a woman from the Salasaca population, belonging to the Tungurahua province in Ecuador. From there, new audios were created with 3 different voices. To increase the number of audio, 3 two-syllable words were selected whose intonation used the African phoneme Chusu, Akcha, Chaki. Then, through the Edge Impulse platform, the features are extracted and the model is trained to finally deploy it on the CLBLE Sense and Nano 33BLE Sense boards. As for the technology used, we have the Nano 33BLE Sense board, the CLBLE Sense board. How did we do it? Through the Edge Impulse platform, audios from 5 classes were loaded, such as 2 minutes Wakcha, 2 minutes Chaki, 2 minutes Chusu, 2 minutes 60 seconds for noise, and 8 minutes for other conversations in Quechua. Regarding training, the GOVEAS classification model was used with 80% data for training, 20% for testing, with 300 epochs in the number of cycles.
The motivation. The dominance of smart devices have enabled remote or autonomous control in some areas of service for people. For example, is in healthcare. Audio recording is an essential component that this device analyzes by detecting voice activity and classify into identities so events like count hit in human speech. However, this device results in frequent false positive when distinguishing in human speech from other sound events. That's it. Its performance is limited to a controlled environment for a specific application. One study found the device yield false positive result for no voice, 16% or 14%, while maintaining a high level of true positive for speech, 89%. Therefore, it's important to note that the false positive rate in voice recognition alert system can have important sequence. Next.
So based on the motivation to contribute to the preservation of these minority languages and the need to improve the effectiveness of voice recognition alerts, it has been considered to build this model with keyword in Quechua language, with the objective of reducing false positive and being able to be used in cases such as an application that was developed to prevent possible femicides by activating emergency voice alerts. For example, it is important to ensure that the alerts reach the people who will provide timely assistance in case of aggression. These people will receive text messages and calls requesting necessary help. What benefits are obtained? First, greater inclusion and accessibility. 2, improvement in the effectiveness of alerts. And 3, a strengthening of cultural identity. As a result, an accuracy of 96.8% was achieved in the training phase, and the 94.12% in the testing phase.
This test is with the Xiao sense. First, we detect with the word in Quechua Wacha. We have an accuracy of 0.99, the word Chaki and it has an accuracy of 0.91. And finally, the word Chusu, which 0.99 accuracy. Then, with the Nano 33 Belén sense, in the same way we tested with the word in Quechua, Wacha. We have an accuracy of 0.94. With the word Chaki and it gave us an accuracy of 0.92. And finally, the words Chusu, which accuracy of 0.98. We have seen that when capturing the words, the nano device took a few seconds longer than the Xiao 2 identity dent. However, the model works with both boards. We have detected that with the word Chusu and Wacha, there is higher percentage and accuracy. With this, the example we consider a future step that we could continue to improve the model and make it as reliable as possible, creating a larger dataset with those words.
Future work. Our intention for the future is to execute more than 1 or 2 models, such as a gender classification model, sentiment classification, or a speaker identification model, which will allow us to know the situation or environment in which a person is in need of timing assistance. And deploying these models on microcontroller using TinyML technologies such as the NICLA voice board. 2, learning and strengthening the Quechua language, and security and surveillance.
Conclusion and recommendation. 1, increase the size of the dataset. 2, explore different machine learning algorithms. While the current approach was successful, it may be benefits to explore different machine learning algorithms that can further improve the accuracy of the model. 3, collect data from different dialects. Quechua have several dialects, and collecting data from different dialects can improve the accuracy of the model in recognizing words from out of them. 4, test the model in real-world scenarios. And finally, it recommends to test model in real-world scenarios to assess its performance and identity any area for improvement.
Thank you for your attention.
That was really good. I posted a question in the chat. I may have missed it in your presentation. What is the translate? I think you were training on 3 main words. What's the English translation? You're muted.
Karina, I think that you are in mute.
Good morning.
Or Jonathan.
Good morning.
Morning.
The translation of the three words is, for example, Wakcha is meaning is poor. Chaki is meaning food, and chusu is meaning thing.
Why you choose these three words, Jonathan and Karina? It's because these are different in terms of sound.
Repeat, please.
Now, why you choose those three words is because the pronunciation, they are different from the normal words?
Yes. This word is particular pronunciation and habitual pronunciation Spanish in Ecuador.
Jonathan, if you want, Jonathan, si quieres, yo te traduzco y después le devuelvo a ellos. Marcelo and Jeremy, if you want, I can probably translate to Jonathan and can help you with the answers.
Okay, fantastic.
So Jonathan, the question, la pregunta, Jonathan, es ¿por qué escogieron esas palabras específicamente? Si es que hay una diferencia fuerte en la pronunciación o cuál fue la razón por escoger esas palabras.
Sí, habíamos buscado palabras, la mayoría de las palabras de Quechua tienen entre 2, 3 y 4 sílabas. Y habíamos cogido estas palabras porque tienen 2 sílabas, lo que mejora el modelo en cuanto a al reconocimiento de voz.
Okay, so it's just because they were short words, just 2 syllables, and probably it's different sound between each other. Y son diferentes en sonido, más o menos, ¿verdad?
Bueno.
Okay.
No, fantastic. No, thanks a lot, Bio. Thanks, Jonathan.
Don't worry.
One thing that I like it, I think it's very interesting because, and I can imagine when you show the device here for female protection. So when you use a kind of alert word in Quechua, I suppose that is not common around the Spanish that you can see around, and you reduce the false positives, and you can also stand the alarm. So it's very clever. I like it very much. One suggestion, Jonathan and Karina, when you said that you have a forced class, you training with another casual words, I think that you also should train against normal Spanish words, mainly for the alarm project. So to be very sure that there's no kind of a Spanish pronunciation word that can trigger your Quechua word. But I think I like the project. I like to see the project going on because it's very important.
Sí, Jonathan, la sugerencia es básicamente que de pronto probar también con palabras en español que suenen parecido para que no vaya a disparar, digamos, la alerta de manera errónea cuando alguien pronuncia una palabra en español que suene similar. Or just translating the suggestion, Marcelo.
Thank you.
Thank you for the situation.
There is a question, why only 3 words? And I can help with the answer, but Diego, you could try translating that. And I think Andrew has a question.
Jonathan, ¿por qué solamente 3 palabras? Es la pregunta. Jonathan o Karina.
While waiting, go ahead, Andrew.
Bueno, al principio teníamos escogido realizar un corpus más amplio con más palabras, pero hicimos una prueba de concepto con respecto a cómo se generaría todo el modelo con 3 palabras en el Engine Pulse. Normalmente en proyectos se han realizado en el Engine Pulse no con muchas palabras, sino con pocas, y realizamos una prueba de concepto con estas 3, que son particularmente única en cuanto al idioma de Quechua de la comuna Salasaca.
Okay, so they wanted to have like more classes, more words, but I guess this was just an initial proof of concept that they wanted to try with H-Impulse with just 3 classes, and that's it.
Yeah, only to complement a little bit, and this is very important question. And as Jonathan said, in fact, not because of H-Impulse itself, but as much class you have or much words you have at the output of your model, bigger is your model. And you should remember that at the end of the day, we are working with a TinyML model. Working with sound, they convert sound to image, okay, for type of spectrogram image, and you classify those images using convolutional neural network. So this is, you should keep this more or less small. With 2 or 3 words, you have something around 50 kilobytes of needed SRAM to run your model during the inference. If you have, for example, 10 words, probably you have, I don't know, more than 100, 150, something like, and usually it will not fit in those kind of small devices. Those devices like the Xiao or the Arduino Nano, they have 256 kilobytes of SRAM. But you should have inside your model a lot of things, not only the model. You need to have the parts to convert the sound, you have a buffer, you have the post-processing. So usually the model should not be more than half of the run that you have inside your model. So that's because you need a small amount of words, means a small amount of model, it means a small amount of memory RAM. Only to complement. Andrew?
We're getting close to the end here. I think Andrew has a question, and then we should be on.
Thank you. This is really cool. My question is, so what service do you use to connect it up to a text message? Because you were saying that when you say it, it sends to a text. Is that correct?
Andrew, what service is the answer? The question, I'm sorry. Jonathan, preguntan qué servicio se utilizó, digamos, para conectarse, digamos, que estás hablando como mensajes de texto, no sé, de pronto aclarar un poquito esa parte, o Karina, no sé.
Utilizamos un sistema open source de Twilio para enviar mensajes. Más bien consumimos su API, que es gratis, y esa fue la forma en que podemos conectar las señales para que cuando lo detecte envíe estos mensajes automáticamente.
¿Son mensajes de texto?
Sí, son mensajes de texto. También probamos como llamadas, porque también se puede realizar llamadas, y sí funciona también. Mensajes y llamadas también.
They use an open source library to send text messages, SMS. But they also try with voice calls as well.
Only to complement, I think that I understood what they did. The device sends, for example, using Bluetooth, because the microcontrollers use it, the Nano and the Xiaos only has Bluetooth. So the same way we saw in previous examples. So what they did, they send let's say the alarm results of the inference using Bluetooth to a device, to the app that they have developed in the cell phone, like a bridge. And the app was connected with a normal, they use an app with a test or can send a voice, etc. But was the cell phone that does this. Okay, this is important.
Great presentation. Thank you so much, your team there. I think, Marco, we should be moving on.
Hello, everyone. My name is Hadiza Yusuf. I am a master's student of engineering and artificial intelligence at Carnegie Mellon University, Africa. And I'll be presenting a project proposal titled DTMF Demodulation, a brief investigation of machine learning for digital signal processing. The outline of my presentation as follows. I'll talk about the background of DTMF, its application, detection, our proposed experimental setup, our proposed performance evaluation, then I'll conclude. Dual tone multi-frequency commonly known as DTMF signaling, is a widely used technique with diverse application in various fields. It was first developed by Bell's lab for the purpose of automatic long-distance call to replace conventional telephone call back in the 1960s. It was designed to send control signals within a voice band. Now, each tone is used in identifying a push button on its DTMF keypad. A DTMF keypad is what we can see on the left side of the screen. It has 16 keys, with each key formed by combining two sine wave tones, one of which is a low frequency sine wave and the other a high frequency sine wave. As you can see, the rows having low frequencies and the column having high frequencies in and these frequencies are combined to form unique keys, which are not being confused with other keys. So the significance of DTMF on telephones has decayed over time due to separate control channels in cellular transmission, but their association with the keypad has kept them alive for many applications today, which we're going to see. Some of the applications of DTMF are in smart home automation, where DTMF-based technology is used to control various devices such as light, heating, ventilation, air conditioning, the movement of gates and doors, and even in security systems. Another application of DTMF is in mobile controlled robot. So the DTMF is keys on a telephone or a mobile phone is keys on a mobile phone is mapped to different movements that a robot can make or operations that it can do. And then when a key is pressed, the sensor on the robot is able to detect what instruction is being given to the robot. Or DTMF can also be used for interactive voice response in banks for customers to access their account information or to make transactions. It can also be used in emergency services to identify the location of a caller and dispatch emergency responders. DTMF can also be used in military communication system to transmit encoded messages and to control remote equipment. It has many other applications in industries. So over time, classical algorithms have been used to detect DTMF. One of which is commonly used is known as the GUDA algorithm. The GUDA algorithm is a mathematical algorithm used to find the presence of a particular frequency in a given signal. To understand this in simple terms, imagine you are in a concert and you want to know if a guitarist played a particular note in a song. You do that by focusing your attention on that particular note and counting the number of times it played, that note is being played in the song. So in a similar way, GUDA algorithm works by focusing on a particular frequency in a signal and also counting the number of times that frequency appears in the signal. And if it's able to detect a chunk of that frequency, then it can conclude that that frequency is within the signal. So compared to other classical algorithms, GUDA has been found to be very fast, but even faster than fast Fourier transform. But it is not robust to distortion or noise. And we know that in real situations, audios or signals, when signals are being transmitted, we cannot avoid distortions or noise, and this is the reason for wanting to explore the use of machine learning models in detecting DTMF. So our proposed experimental setup is we will be using PC as our modulator and an Arduino NanoSense, which has a microphone to receive audio signals, and it would be our demodulator. So the PC will be used to generate two frequency signals simultaneously, for a brief interval of time, and each of such transmission is one symbol. So at every interval of time, 4 bits will be sent by the sender, which is our PC. So the process of mapping bits to symbol when encoding is called modulation. For example, we have vertical frequencies and horizontal frequencies here. So this one vertical frequency and one horizontal frequency forms a symbol, and converting that symbol to bits is known as modulation. Then the modulation is what the decoder does to determine which symbol was sent. So we will generate our training data on the PC synthetically. At first, we would use perfect symbols without distortion. Then later on, when we're able to get the system working, we can now start distorting the symbols by adding different noise to them. Another way we hope to get data sets that includes distortion is to capture our training sequence with an Arduino, where signals are being generated on the PC, and then we play them, and the Arduino receives them as audio signals. So with distortion from the environment. So this would be done after 2 systems are being synchronized. So after that, we will run an ML inference, specifically TensorFlow Lite, and then this model will classify received signals and predict which of the 16 classes corresponding to the 4 bits was sent. So to evaluate our model, we are going to be answering these questions. We'll look at how small of an ML model can be used to get a reasonable performance, and then we'll check how fast we can send bits from the PC to the Arduino using the TMF. And then we'll also look at if our synthetically generated training sets perform as well as the training sets we captured with the PC and Arduino combination. That's the training set that has distortions in it. And then finally, we would also compare a classical model with our model, with our machine learning model, and see which one performs better and which one also shows more robustness in the presence of noise like speech and music. So in conclusion, we hope that this investigation will provide valuable insights into the potential use of TinyML for DTMF demodulation, as we have seen that DTMF is important in several applications. So we look forward to sharing our findings. Thank you.
And very good presentation. I think Jeremy just left just for a second. So any questions?
I think there was a question, but there was wanted to confirm that your tests you using the nano BLE sense, correct? Because you have the microphone, correct? Not the BLE only, no?
Okay, thank you very much. Yeah, it's an Arduino 33 BLE sense.
Okay. And we have Andrew that has his hand raised. So Andrew, do you want to ask your question?
Yeah, this was interesting and cool. And I guess I'm kind of curious. I think I might be misunderstanding the DTMF itself. Is the DTMF an application layer that just emits a certain sound when you push a button? So it's like any keypad, any normal keypad emits the same sounds. It's like is DTMF the standard sound that it emits through a board? I think I'm a little confused.
Okay, thank you for the question. DTMF is actually the mixture of those signals which was on the slide. There are actually standard frequencies that have been used so far, but I think other frequencies could also be.
I think that you cut your sound.
Yeah, I think it's. These are the sound is not there, but I looked for it, Andrew, on Google, and I found this answer. So it's a technology used with touchtone phones. Yeah, I think we lost.
We lose her.
Aliza, yeah.
Sorry, I disconnected just a bit.
Okay.
Okay.
Yeah. So I was saying that the system itself is what is called DTMF. That's a combination of those frequencies. So just like our previous phones that are not screen sensitive, that has keys. So each of those keys produce a unique tone, which is a combination of those high and low frequencies. I don't know if that answers the question.
It does. Thank you.
No more questions. Then thank you very much. That was very interesting. Another round of applause for you. And well, those were 8 super interesting and diverse applications. I think that is how we selected them. Before giving a final word to Marcelo, just again a reminder, and Jeremy, if you want to comment on that, if you're available, we have this monthly show and tell event. So next one will be, I believe, the 25th of May, and they're really well attended. Similar to this event, lots of people, very nice comments. So if you have any projects concerning TinyML, even in the initial phase, so they don't need to be, complete projects. If you have an idea, you want to pitch it just for 5 minutes, we have 5, 10, or 15 minutes presentation. So very, flexible. So please get in touch with us, and we can reserve a seat for you. And I think that's all from my side. Marcel, if you want to join, do you want to add anything?
Thank you. No, first of all, I mean, I'm very, very glad. I think that saw today great presentations, great projects, from all over the world, from Latin America, from Africa, from Asia, students, a lot of female students and researchers, people. I mean, it's very nice. I hope that all those projects continues. People, be excited to go further, to learn or to implement the smaller project, smaller models inside smaller devices, because that's what we're talking about, to develop applications that can be fit in very small devices using very low power, that it can, works longer, and that in cheaper way, when you can put this application in health, in agriculture, like I saw today, when you don't have a lot of communication bandwidth in the most remote areas, and that's where TinyML can use it. I would like to say goodbye for you guys today, because I'm not available tomorrow. I will be traveling tomorrow, but I'm very happy to stay with you guys till today during all the week. Together with Marco, with Brian, Jeremy, and Vijay, we work together at the TinyML4D. That our goal exactly is to take the embedded machine learning knowledge, and bring this knowledge for us to developing countries in Latin America, in Africa, and Asia. This is our goal, and to work among us. This is very important. Let's create a network. Let's work together. Let's take our universities and exchange ideas, exchange projects. This is fantastic. So let's do this, and count on us. Count on me. I'm always available at the Discord. You guys have my email. I have my GitHub. I gave a lot of my contacts in my speech Tuesday. So thanks a lot, and see you in the next event next year, or this year. I hope so. Bye bye.
Thank you very much, Marcelo. Thank you very much for all your help. And yeah, as Jeremy said, we have been working on this for long, right? So we're really happy about how this activity went so far. Again, don't forget, tomorrow we're going to cover advanced TinyML applications. So that will be very interesting. And so see you tomorrow, same time, same Zoom room. Take care.
Bye-bye, guys.
Bye-bye. Bye-bye.